See it?
All right, great. So I'm Emma Batson, and I'm talking about transparent superconductors and how we can use those for more efficient transduction. So, microwave to optical transduction is really important to our goals here. It's necessary for transferring quantum information from a superconducting computing qubit that might be in the microwave regime to an optical communication qubit. And we have a design that we've worked with Marco Loncar's group. They've got this design where you use superconducting electrodes to couple these microwave modes to the optical modes in a ring resonator. Here's a cross section of what that might look like. So in the middle here, we have our lithium niobate optical resonator surrounded by the silicon dioxide substrate. And sitting on top of all of that, we have these superconducting electrodes. Most of the optical field will be really well confined to the lithium niobate, but as always, some of the evanescent field is going to persist in our dielectric. Any optical field that's absorbed in these superconducting electrodes will lead to losses, as is discussed, I think, in an earlier talk. And that leads to weaker coupling and weaker transduction. So, how can we fix this? First, we'll talk about refractive index and dielectric loss. We're going to have a complex refractive index where the real part just leads to, the classical sort of bending stuff. And then this imaginary extinction coefficient leads to absorption and dielectric loss. So the higher that is, the more absorption we have. Most superconductors are going to be really highly absorptive in optical frequencies because they're metallic. But what if we could make a transparent superconductor? There's a great paper that goes through the process of this. Basically, you can take an optically transparent, highly conductive material and intercalate it by putting something metallic, like a sodium ion, into vacancy sites in the crystalline structure. This gives the whole material, in this case, indium tin oxide, some metallic properties with only a bit of loss of transparency. There's actually a trade-off that's seen in this chart here between the threshold temperature and transparency. The threshold temperature peaks at this point where it's become pretty opaque. But if we're able to tolerate a lower threshold temperature, we can actually have something that's quite transparent. For ITO, the refractive index is about 1.83. I don't know how this changes with intercalation. And we've estimated from samples, old samples from our lab, that the extinction coefficient is about 0.36 based on this equation at the bottom. Now, we can quantify this loss using a Comsol simulation since we have all this refractive index information. If we assume that the electrodes are just a small perturbation to the system, then we can just do a Comsol simulation of the full system and the system without the electrodes and compute the quality factors of both of those in order to extract the quality factor of the electrodes alone. When we do this, we see we have a super high quality factor when there are no electrodes to take in this optical absorption. And then we can look at the effect of using different materials for the electrodes. Our intercalated ITO electrodes, we estimate, would have a higher quality factor than niobium nitride, but actually a lower quality factor than just niobium. So what's up with that? Well, we can see that the niobium electrodes have a refractive index that's really different from that of silicon. So even though it has a pretty high extinction coefficient, a lot of the optical light is actually getting reflected, is my guess. So let's see, can we improve our transparent superconductor? First, I'd like to get better measurements for the actual N and K values using ITO that we'll newly produce in the lab. Maybe we'll learn that it's better than we think. But again, there's this trade-off between the threshold temperature and transparency. With just a 10 times reduction in K, we could get the quality factor up to above that of niobium. Also, if we had a refractive index that's actually much more different than silicon dioxide, we'd get more reflection, and that could improve the quality factor even without being able to reduce the extinction coefficient at all. So I think the outlook on this is that transparent superconductors could be a pretty good way to reduce losses and improve transduction efficiency in these microwave to optical transducers. So thank you.